Let's try a more rigorous problem that is going to combine Unit 5 and Unit 3 together. A 62 kilogram skier is pushed off from the top of a ski hill, accelerating down at 1.889 meters per second squared. She is clocked going 42.7 meters per second at the bottom of the hill. First thing we want to know is how long does it take her to get to the bottom of the hill? So let's list out the knowns. We've got the mass of 62 kilograms. We've got that she is accelerating at 1.889 meters per second squared. She starts at rest at the top, and she is clocked going 42.7 meters per second at the bottom. And we want to know, what is the change in time? Now this one, we don't have to use both Unit 3 and Unit 5 yet, because if you notice, ultimately we're looking for time, and we have acceleration, velocity, initial velocity, and final velocity. You know, in Unit 3, Unit 5 combo problems, we don't have the acceleration, but since it's given to us here, we can just use everything we know from Unit 3 in order to solve this. So let's use VF equals A delta T plus VI. Our final velocity was 42.7 meters per second. That has to equal 1.889 meters per second squared. We're going to be looking for that time, and her initial velocity was 0 meters per second. So when we do the algebra here, we find that the change in time of this skier is 22.6 seconds. Fantastic. Part B. If the friction force between her skis and the hill is 168.4 newtons, what is the angle of the hill? So this is now talking about forces. So we've got a lovely picture of this lady. Let's draw a quick force diagram. First, there is a force of gravity pointed down. There is a normal force from the hill that is pointed perpendicular to the hill, and then there is a force of friction that is going up the hill, and they tell us that this is 168.4 newtons. So keep that in the back of your mind. Now, something else to remember is whenever we have a problem where someone is on some kind of a hill, we change how we look at the problem so that we are looking at things that are parallel or perpendicular to the hill. So our force of gravity needs to be broken up into the parallel component of the force of gravity, which can be found by doing Fg sine of theta, right? Because the theta of the hill is right there. And then there's the perpendicular component of gravity, which is Fg cosine of theta. We'll want those later, especially because Fg cosine of theta is always going to be equal to Fn. That might be useful. But for now, we want to know if the friction force is 168.4 newtons, what is the angle of the hill? So since we know something about friction, we know something about the direction that she's accelerating, so we might as well do a net force equation. So let's look at all the forces that are going either up or down the hill. The one that is going down the hill is Fg sine of theta. Force of friction is going up the hill, and to show that change in direction, I'm going to give it a nice subtract instead of add. And together, these two things have to equal ma. Well, let's fill in everything we know. We know that Fg is equal to 9.8 newtons per kilogram times mass, which is 62 kilograms, times the sine of theta. And you know what? We don't know what theta is. That's what we were going to want to find. The force of friction is 168.4 newtons, and this has to equal ma. So I think our acceleration was 1.889 meters per second squared. So great. After we wrote this net force equation, when we sub in all of the numbers that we know, the only number that we don't know is theta, which is what we're going to be looking for. So what we can do is we can try to simplify this a little bit. So 9.8 times 62, well, that is 607.6 sine of theta. And I'm going to go ahead and add that 168 times or sorry, we're going to add that 168.4 to the other side, so that when it is added to 62 times 1.889, we're going to end up getting what should be on the right-hand side of the equal sign. So that should be 285.52. Next, we need to divide both sides by 607.6. 607.6, so that we're able to see that the sine of theta should be 0.4699. Now, if you remember, we need to do inverse sine in order to get rid of this, so we'll just do inverse sine on our 0.4699, and we end up getting that the theta should be 28 degrees. Cool. Let's go into part C. How far is it from the top to the bottom of the hill? So this is really asking us, what is our delta x? We have a ton of information. I think we would be able to find our delta x just by using everything we know from Unit 3. So let's use a fan favorite. Let's use VF squared equals VI squared plus 2a delta x. Our final velocity is 42.7 meters per second. We'll square that. Our initial velocity is 0 meters per second. Our acceleration is 1.889 meters per second squared, and then we need to solve for that lovely delta x. So as you guys can see, some of these problems, we're just kind of flipping back and forth between Unit 3 and Unit 5, which is totally okay. Anyway, once we put that into our calculator, we find that delta x ends up being 482.6 meters. That's how long this hill is. And finally, let's do part D. At the bottom of the hill, she slides along a flat horizontal surface and stops. If the coefficient of sliding friction between her skis and the snow is 1.14, how long does it take her to stop? Well, that was a lot of information. I need to write that out in the knowns table. At the bottom of the hill. Well, at the bottom of the hill, we know that she is moving at, what was it, 42.7 meters per second. She's going to slide along a flat horizontal surface and stop. So our final velocity is going to be 0 meters per second. The coefficient of sliding friction is 1.14, so our mu is equal to 1.14. And we want to know how long does it take her to stop. Well, actually, maybe I should add some stuff that we already know about her. We know her mass is 62 kilograms. And I suppose that might be it. All right, so now we want to know how long is it going to take her to stop. This looks like a real Unit 3, Unit 5 combo problem, because you've got your stuff about motion. We've got our stuff that deals with forces, and we are not given an acceleration. So that means that the first thing we should do to solve this problem is probably try to find acceleration. But what should we do? Should we use Unit 3 stuff, or should we use Unit 5 stuff? I think we should use Unit 5 stuff, since we're looking for something that pertains to Unit 3. So our first step is going to be find acceleration using F net equals ma. So when she's slowing down, she's got a force of gravity pulling her down. She's got a normal force pushing her up. And since she's on horizontal ground, those two things can be the same. Now there's the force of friction between her skis and the snow, and as far as I can tell, that is the only force in the x direction. So when we write our net force equation, Our unbalanced force is the force of friction, and so that has to equal ma. We know that the force of friction is equal to mu times Fn, and we know in this case our Fn is the same thing as Fg, so we could put in 9.8 newtons per kilogram times mass, oops, instead of writing Fn. So now we can put numbers in here, because I think we know all these numbers. We've got mu is 1.14, then we got our 9.8 newtons per kilogram, and then our mass is 62 kilograms. This has to equal 62 kilograms times our acceleration. Now when we do the algebra, we end up getting that our acceleration, wow, it's kind of big. Bigger than that. But it's 11.172 meters per second squared. That was really fast. That's like faster than free fall. But hey, apparently this snow is really sticky. Okay, next thing we want to do is we want to figure out how long is it going to take her to stop. So let's use kinematics, aka motion, to help us find delta t. So if we look, we've got VI, VF, delta t, and A. The equation that has all of those together is VF equals A delta t plus VI. So our final velocity was 0 meters per second. Our acceleration was 11.172 meters per second squared times our mysterious delta t plus 42.7 meters per second. Now, she's slowing down, so we know that our acceleration and our velocity are in opposite directions. So I'm going to go ahead and add a negative sign to that 11.172. And then we just need to do the algebra. And once you do the algebra, you end up getting that the time it takes for her to slow down is 3.82 seconds. Now, this is a very interesting problem, right? We had 4 different parts, and some parts purely were able to be solved by Unit 3. Some parts we had to use all of our knowledge from Unit 5, and then the last part we had to put them both together in order to help us solve. Okay, so when you guys are doing your homework or taking a test, make sure that to write out all of your knowns, and if you notice that some of your knowns are from motion and some of your knowns are from forces, don't be afraid to use both units of knowledge in order to help you solve this problem. Good luck!